Hi everybody, welcome back to this course on Internet Technologies. I'm Vardan and today we'll be studying about port numbers and connection establishment. So let's start by understanding where TCP and UDP actually fit in the bigger picture. In the TCP IP protocol suite, the transport layer sits above the internet layer. While the internet layer takes care of getting data from one device to another using IP addresses, the transport layer takes care of getting data from one specific process on one device to a specific process on another device. To do this, it relies on two main protocols, TCP and UDP. Both use the underlying services of IP to move data, but they handle the details very differently. And here's something very crucial. Since multiple applications can be running on the same computer at the same time, the system needs a way to tell which incoming data belongs to which application. And that's where port numbers come in. Port numbers act like an address for each process on a machine, letting the transport layer deliver data to the correct application running at the user level. Now let's talk about TCP or Transmission Control Protocol. TCP is a connection oriented protocol. That means before any actual data transfer happens, TCP sets up a connection between the sender and receiver and only then starts sending data. It's designed for reliable data transfer, which means it guarantees that all the data you send will arrive at the other end correctly and in order. It provides a full duplex byte stream service, allowing data to flow in both directions simultaneously. To achieve reliability, TCP uses a combination of mechanisms. It uses a checksum to detect errors in the data, acknowledgements or ACKs to confirm receipt of data, timeouts to retransmit lost packets, flow control to prevent overwhelming the receiver, and sequencing numbers to reorder any packets that arrive out of sequence. Besides all this, TCP is responsible for properly establishing and terminating connections. This makes it ideal for applications where data integrity and order are critical, something like web browsing, email, or file transfers. On the other hand, we have UDP or User Datagram Protocol. UDP is a connectionless protocol, which means it doesn't set up a connection before sending data. It just sends the data and moves on. No handshakes, no checks for whether the data arrived. And it's much simpler than TCP, and because of that simplicity, it's also faster. However, this speed comes at the cost of reliability. There's no guarantee that your data will arrive, no reordering of out of sequence packets, and no retransmissions whatsoever if something gets lost. That said, UDP does improve on raw IP in two ways. It adds a checksum to help detect errors in data, and it uses port numbers to help deliver data to the right process on a device. UDP is used where speed is more important than reliability, like in video streaming, online gaming, or real time voice calls, where a few packets lost doesn't matter much. Now let's dive deeper into port numbers. On any given device, there could be several applications using TCP or UDP at the same time. So, how does the system figure out which packet belongs to which application? That's where port numbers come in. A port number is a 16-bit integer, meaning it can have values from 0 to 65,535. It acts like a virtual endpoint for each process running on a machine. And when a packet arrives, the transport layer looks at the port number in the TCP or UDP header to decide which application should receive that data. This way, you can have a web browser, a mail client, and a file transfer application all using the network at once without any confusion. Let's make this a bit more real with a client server scenario. When a client wants to connect to a server, it uses the server's 32-bit IP address to find the correct machine and a port number to target the specific process on that server. For example, if a client wants to access a web page, it connects to the server's IP address and typically to port 80 for HTTP or port 443 for HTTPS. When the server responds, it sends back to the client's IP address and port number. This system allows multiple applications on the same service. For example, thousands of users can be connected to port 80 on a web server at the same time, and the server keeps track of each connection by looking at the combination of client's IP and port number. Now, here's an interesting detail. Not all port numbers are assigned the same way. Certain port numbers are well known and publicly assigned for standard services. For example, port 21 is for FTP, port 25 is for SMTP, and port 80 for HTTP, and so on. But when a client connects to a server, it also needs a port number so the server knows where to send the reply. Instead of using a fixed number, the client asks its local operating system to assign a temporary port number for that connection. These temporary ports are called ephemeral ports. Traditionally, ports 1 to 1023 are reserved for well-known services, and numbers from 1024 to 65535 are available for these dynamic assignments. So every time you open a new tab in your browser or start a new app that uses the network, your operating system assigns it a temporary port from this range. Now, how do we precisely identify a connection between two processes across a network? This is done through a hierarchical addressing scheme. At the bottom, we have the IP address, which identifies the device. Then we have the protocol identifier, TCP or UDP, and then the port number, which identifies the process on that device. When establishing a connection, especially with TCP, we actually use a combination of five values. It is called a five tuple association, and it includes the protocol being used like TCP, the local machine's IP address, the local port number assigned to the process, and the remote machine's IP address and the remote machine's port number. For example, a TCP connection might be described as TCP 144.16.192.5, 1785, 144.15.202.57, and 21. So this tells us everything about where the data is coming from, where it's going, which protocol is handling, and which applications are involved on both ends. That's how networks manage process to process communication with precision. And with that, we've come to the end of this lesson. And in the next lesson, we'll learn about TCP and UDP segments and the Berkeley socket interface. So thank you for joining in, and I'll see you next time.